right, let's get started. Everybody got the lecture exam 4 study guide? You remember how long the lecture exam 2 study guide is? Like 5 pages. Yeah, this is 11. This is where we pile on all the organ systems in one lecture exam. Because we went so slow for 3/4 of the semester. Did you think that we were going fast? We went so slow for 3/4 of the semester that we have to pile on blood and circulatory system, lymphatic system, respiratory system, digestive system, urinary system on page 7. Finally getting the reproductive system starting on the bottom of page 8, which takes us all the way through to page 11 where we talk about delivery and early development delivery. So I would strongly recommend that you pay attention to things only that are highlighted, underlined, and bolded, because it's a lot of material. Okay? There are students that pass lecture exam 4, especially those that have been building up dendritic spines in their hippocampus all semester long. But you have to keep in mind that lecture exam 4 is entirely Scantron. There are no essays. So if Scantron questions were weekly, hopefully you have been improving over this semester. Okay? All right. Lab exam 3s are this week, lecture exam 3 is next week. Here we go. We'll start on blood. First, the main functions of blood. Yes?
Are you also going to go back to those other slides that you didn't go over?
What's that?
Are you going to go back to those other slides that you didn't go over last week?
You told us to bring them Thursday, we ran out of time.
Oh. No, I wasn't gonna do that. But now, yes, I will. Oh, you're a hustler. Turning here, right? Pituitary glands. So this is a real important endocrine glands. So only when I really spend a whole lot of time on it. This is my hypothalamus. As we learned in the lab, the pituitary gland is 2 glands in one. You got the anterior lobe or anterior pituitary and the posterior pituitary. The reason why it's 2 glands in one is they have different embryonic origins. Early on in embryonic origin and embryonic development, there is no skull. This is before there's even a skull. And there's going to be a little upgrowth out from the roof of the mouth and a downgrowth from the diencephalon. Eventually, this upgrowth from the roof of the mouth is called Rathke's pouch. It gets really elongated, then it actually pinches off, wraps itself around this little finger of diencephalon, like that. Everybody see the sequence? Then the skull starts forming. In fact, right around this area is the sphenoid bone. What structure of the sphenoid bone goes around this little punchy bag? The sella turcica. That is what now is gonna form around this thing, and that's why the sella turcica is shaped that way, because that thing was there first. Everybody got it? All right, well, this is why when we look under the microscope at the pituitary gland, why it looks this way. The anterior pituitary gland looks like a glorified spit gland. It came from the roof of the mouth. The word for, or the root word for gland is adeno, so we call this the adeno hypophysis. Hypophysis is pituitary. The posterior pituitary, when we look at it under a microscope, looks like a nerve trunk, because that's exactly what it is. Axons and axon terminals only. So we call the posterior pituitary the neurohypophysis. Everybody got it? Does that make sense? It makes sense only because if you know where it comes from in the embryo, which is why when I was at San Jose State, very last semester I was there and I'd already been accepted into every dental school I'd applied to, so I was cruising the last semester. They said, you know, you just gotta pass these classes. You don't have to worry about your grades at this point. I still got straight A's. The last semester I took comparative vertebrate embryology. It was loaded with nothing but pre-medical and female students. And I was so sorry that I waited till the end to take it, because taking that class, everything made sense. How the body organs looked, how they functioned, everything made sense. Like this, when you figured out where the anterior pituitary comes from, it makes sense that it looks like a glorified spit gland. Right? When you know where the posterior pituitary comes from, it makes sense that it looks like a nerve trunk. Everybody got it? All right, well, this relates to how the hypothalamus controls the pituitary gland, because since there are two different glands, there are two different ways the hypothalamus controls the pituitary. For the anterior pituitary, the hypothalamus will actually send hormones in this very short blood vessel. Now this week in lab, we are going to learn what a portal vein is. And it's different. Okay, so we had lab last week. Do you guys remember lab last week? Mm-hmm. Well, in the systemic circuit, right? Systemic circuit, arteries are red, veins are blue, correct? You go artery, arterial, capillary bed, venule, vein, back to the heart. Does this make sense? They had that one picture that showed both circuits, pulmonary circuit and systemic circuit, and then that figure in the lab PowerPoint showed all the red arteries going into this capillary bed where it turns blue. Then it goes into veins back to the heart, correct? The sequence is artery, arterial, capillary, venule, vein. Shall I repeat that?
Yes.
Artery, I should write it down. That is the classic sequence in the systemic circuit. When you have a portal vein, it's different. Anybody got this? Okay, I went to a birthday party yesterday, so you guys gotta be kinda keeping up enthusiastically, because I'm missing enthusiasm right now. Okay, you guys ready? Portal vein goes this way. Artery, arterial, first capillary bed, venule, portal vein, venule, second capillary bed, venule, vein, back to the heart. In the case of a portal vein, it is the vein between two capillary beds. Do I need to repeat that?
Yes.
Artery, arterial, first capillary bed. So I'm not gonna write it on. Venule, portal vein, venule, second capillary bed, venule, and then vein, regular vein back to the heart.
So wouldn't it be between two venules then?
Yes. It would be, but it's between two capillary beds. Just
Okay,
think of it between two capillary beds.
okay,
And yeah, there's two venules in between that too. It's between two capillary beds.
okay.
Especially because we're gonna learn about them. There's two of them in your body. There's the big one in your digestive system. We're gonna learn about that this week in lab. The hepatic portal vein and the hepatic portal system. What's on the screen right now is the other one, and it's the small one. And it's the hypothalamo-hypophyseal portal system. So here we go. You have the first capillary bed. It's going to collect releasing hormones or releasing factors from the hypothalamus. It's going to go through this hypophyseal portal vein to the second capillary bed, come out there to the anterior pituitary, and then those releasing factors sets the anterior pituitary in motion to release other hormones. The anterior pituitary does not release its hormones without releasing factors from the hypothalamus. That has to go through this portal vein. Everybody got how one way the hypothalamus controls the pituitary, and this is on the anterior pituitary. So concentrate this on the anterior pituitary. That's the portal vein. Anterior pituitary. Adenohypophysis is anterior pituitary. And there's a ton of them. In fact, if you look at this list of hormones that come out of the anterior pituitary, each one has a releasing factor that comes out of the hypothalamus that goes into this portal vein. Everybody got it? This controls the thyroid gland. This controls the adrenal cortex. This controls the gonads. This controls the pineal body. Because so many of these hormones control other endocrine glands, on the TEAS test, please answer that the pituitary gland is the master endocrine gland. Because the anterior, all those letters, not all of them, but a majority of those letters represent hormones that control other endocrine glands. The anterior pituitary is known as the master endocrine gland, and it is a lie. But you don't care on the TEAS test. If they're expecting you to lie, just lie. Because is it the master endocrine gland?
No.
It's controlled by the hypothalamus, by these releasing factors. So the hypothalamus should be the master endocrine gland, right? No, it's controlled by body conditions. Oh, body conditions must be the master then, right? No, it's controlled by all the endocrine glands. Well, then all the endocrine glands must be the master. No, it's controlled by the anterior pituitary. So the anterior pituitary must be the master endocrine gland. Yes, for the TEAS test. But it's not, because it's controlled by the hypothalamus. Hypothalamus must be the master. No, it's controlled by body conditions. Body conditions must be the master. No, it's controlled by all the endocrine glands. All the endocrine glands must be the master. No, it's controlled by the anterior pituitary. Anterior pituitary must be the master endocrine glands. Yes, for the TEAS test. Do you see why it's a lie?
Yes.
It's a circle. And the whole concept of the anterior pituitary being the master endocrine gland is linear. It must be on top. Well, it's not on top. The hypothalamus is on top. No, it's not on top. It's all a circle. When you practice medicine, you know what the truth is. And you know that the classes taught at this level, a lot of it is a lie. Just get it right on the TEAS test. Any questions?
So we're just calling it a circle, or is it like one of the feedback loops?
It is a feedback loop.
Negative or positive?
This will be negative feedback loops. loop is a circle, and there's no top to the circle. There is no master. If on the T-test somebody actually corrects it, keep aware of it. If one of the options is there is no master, that's the right answer.
Oh,
But if they don't put that option in there, and it's just, you gotta pick out of what is the master endocrine gland, and the only one on there is anterior pituitary, and there is no master, you gotta put anterior pituitary. Cause that's what it's been. Everybody got it? Wouldn't it be great if everything was just straightforward? Well, you're talking about biology, and the human body is part of it, and there's nothing straightforward about it. So you have to get started in a straightforward manner so that you can understand that it's not straightforward later. Does this make sense? That's what's hard. All right, the second way the hypothalamus controls the pituitaries, this has to do with the posterior pituitaries, so circle that. And there's only two hormones that come out of the posterior pituitary, and that's ADH and oxytocin. Each are only 9 amino acids long. But here's the deal. They are actually not posterior pituitary hormones. They are made in the hypothalamus. Supraoptic and paraventricular nucleus. Oxytocin comes out of here, ADH comes out of here, and it's made in the cell bodies in the hypothalamus, in the gray matter. It's packaged in vesicles, and the vesicles go down the axons to the axon terminals, and they actually kind of look like neurotransmitters in a synapse. And if you are dehydrated or eat too much salt, the paraventricular nucleus neurons are going to fire action potentials. And when the action potential gets back to all the way down to the axon terminal, it triggers exocytosis like neurotransmitters, and it's released like a synapse, except there is no post-synaptic neuron, just capillary. This is a really good illustration of the distinction, the blurred distinction between nervous system and endocrine system. This looks like it's supposed to be a synapse. Instead, it's releasing ADH into capillaries. It'll go down to your kidneys, and you will retain water. Any questions? You guys look a little confused. Is this confusing you?
that one was a little more.
The way the hypothalamus controls the posterior pituitary is these are not posterior pituitary hormones. They're made in the hypothalamus. They're only released at the posterior pituitary where the axon terminals are because it looks like a synapse.
That was better.
Everybody got it? That's why the posterior pituitary looks like a nerve trunk. Because that's all it is axons and axon terminals. Neurohypophysis. Is all this making sense, or am I just speaking Greek?
Makes sense.
Okay. And then this, don't worry about this, but if you ever have to learn all the hormones and how they interrelate, I would use a conceptual map and centering around the pituitary. Because the anterior pituitary, again, a lot of those hormones target other endocrine glands. All right, that's it for electroexamining material. Any questions?
So we don't need to know those ones in that slide though?
No. You will eventually. In fact, I don't even do that in physiology, but you will eventually. When you do, use conceptual. All right, now let's go to electroexamining material. Function slide, what you're supposed to do, Always a question on function slides. Blood is the transportation medium for nutrients and oxygen, waste, and CO2. You know, if you're a single cell like an amoeba, you don't need a circulatory system. You get everything you need from the pond water, but let's just face reality, if you're an amoeba, you shit where you eat. Because you put the same waste in the same water that you just got your food from. Well, this is the circulatory system with the blood is keeping all your amoebas alive, and you've got trillions of them. You gotta deliver nutrients and oxygen, you gotta get rid of CO2 and waste. Most feedback loops, not all, but most feedback loops have some portion of it occurring in the blood and the circulatory system. I'm covering immunology and physiology right now. They have 2 lectures. You have 2 slides. And usually I had to take 2/4 of it. But the immune system definitely uses the blood. All right, let's talk about what makes up blood. If we take a test tube of blood and spin it in a centrifuge, and that's what I wrote up there, spun whole blood, red blood cells are the densest, it goes down to the bottom. This is a connective tissue, which means the cells are separated by stuff. In this case, blood, the cells are separated by plasma. That's the stuff that's separated the cells. And it is the least dense, so it sits on top. Let's talk about what's in plasma. The whole thing sets up like an outline. Plasma at sea level is usually slightly more than half. Let's just go with 55%. It has a normal range. It doesn't have to be 55%. Everybody got it? Everybody got it?
Yes.
All right. In plasma, it is mostly water. Now, when it says 92%, that's not 92% of whole blood. That's 92% of the 55%. You got it? That's what it says up there. Second is plasma proteins. You can call them blood proteins, but they are floating in plasma. So on the screen it's one way, on the whiteboard it's another way. It's the same dang thing. That's about 7% of the 55%. I've listed in this bullet the top 3. Albumin provides osmotic balance to the blood. You guys remember learning about osmosis in the first lecture, Sam? Well, in physiology, you have to know that if osmosis, if water follows the salt, and I said, well, it's water follows anything that's osmotically active, correct? If water follows the plasma protein, it's called oncosis. So this really is supposed to be oncotic balance. But this is anatomy, so you can just call it osmotic. Then you have globulins. And there's a whole bunch, so this includes antibodies. Because antibodies are immunoglobulins. Fibrinogen is a liquid. When you need to coagulate blood, there's a whole system, a whole cascade of reactions that'll turn it into solid fibrin, and that's what gives you a blood clot. But while you don't have that pathways cascade of reactions started, it's liquid and it's floating in plasma. But these are just the top 3. And form most of the 7%, but there are many, many others. And the last 1% is all the other solids, ions, nutrients, and waste. This is there in that bottom diamond, the first bullet on the previous slide. Transportation of all these others. You see nutrients and waste there in the first bullet? You see nutrients and waste there in the bottom diamond? Are you connecting the dots? That's plasma. And then it sits on top and it's slightly more than half. Then we have the formed elements. These are the cellular components. Go ahead and fill in the blanks. Now, they may not be all full cells, but they came from cells. And this is about 45% of whole blood. So when you get all these numbers, you gotta kind of keep it straight. What are you talking about? The 55 and the 45? That's of whole blood.
When you say whole blood, do you mean like when the plasma's in it? Like,
The whole test tube.
okay.
When I'm talking about 92.7 and 1, that's just out of here. Everybody got it? Now I'm gonna do some other percentages, and that's just out of here. The vast majority of formed elements is erythrocytes, red blood cells. This 99.9% is of that. Everything else that's cellular is in this tiny little space that sits on top of the red blood cells called the buffy coat. That was a birthday party on Monday. Okay. All right. Oh, these 1 through 5. These are the white blood cells. So red blood cells are at the bottom. Buffy coat has all the white blood cells. There's 5 of them plus the platelets. Does that help? What's on these? big percentages are of whole blood. I underlined the big ones. All the other ones are either part of plasma or part of the formed elements. All right, let's talk about hemopoiesis. Hemopoiesis means blood cell formation. Hemopoiesis means blood cell formation. How many formed element cell lines are there? Look on the whiteboard and tell me. How many formed element cell lines are there? It's on the whiteboard. Look under formed elements. How many cellular lines are there?
Two or three. Red blood cells, white blood cells, two.
How many are in the Buffy code?
Six.
6.
Oh,
You guys weren't at that party. What the hell? I should be this obtuse right now. Hell, I don't know. How many? Well, if you count the red blood cells, that's 7. There are 7 cell lines. Everybody see that on the whiteboard? 6 in the Buffy code plus red blood cells. There's 7. Now look at this figure on the slide. How many rows? There's 7. Everybody see on the 7 rows?
yeah.
All right. They all 7 start out as hemocytoblast. Hemocytoblast is the pluripotent blood stem cell. Hemocytoblast, pluripotent blood stem cell. It can become any of the 7. This is now, every arrow is a step of what we call differentiation. And it's kind of like when we talked about mesenchyme. Remember, mesenchyme is the pluripotent connective tissue stem cell. All connective tissue cells start out as mesenchyme. Well, guess what? Blood is connective tissue. Hemocytoblast came from mesenchyme. But once it's a hemocytoblast, now it's going to be one of the 7. The next step of differentiation is it's either going to be a lymphoid stem cell or a myeloid stem cell. While the lymphoid stem cell is only going to be one of the 7. And that's this guy here, lymphocytes. You want me to write this all out? Even after a birthday party, you're not going to let me get away with just writing the first letter? Well, this lymphoid stem cell is just going to be this. And so when you see, don't use the term progenitor cell for any of the lymphoid stem cell. Once it's on this first step of differentiation, boom, it is going to be a lymphocyte. These are the cells of the immune response. And so when it says B or T, there's just 2 different types of lymphocytes. There's also NKs and now with the myeloid stem cell, it can become still any of the other 6. And so the next step of differentiation, we will use the term progenitor cell. Everybody see that? So stem cells just 2, lymphoid or myeloid. Lymphoid now is just gonna become a lymphocyte, but the other 6, the next step is gonna be one of 6 progenitor cells. Once it is progenitor cell, it is committed to one of the 6 lines. Which is why progenitor cell is oftentimes referred to in other textbooks as committed cell. You might want to write that down next to this slide. Progenitor cells are also called committed cells because they are committed to one of the 6 other lines.
So are those myeloid or lymphoid ones not committed, like can they change?
They are, well, here's the difference. For the myeloid stem cell line, they are not committed till they get to the progenitor cell. For the lymphocytes, it's committed on this very first step. So we don't use the term progenitor cell for the lymphoid line. Again, once you're in the myeloid stem cell, then you hit the progenitor cell, you are now committed.
Got it.
Okay?
And it commits to anything below it in that list?
Yes, so this will be committed at the stem cell line, the lymphoid stem cell, but the other 6, these 5 plus red blood cells, you have to go to the progenitor cell to be committed. Let's talk about red blood cells, erythrocytes, since they are the most numerous of the formed elements. Primary function is to transport oxygen. Much smaller secondary function is to transport CO2. It does it a lot less. The majority of CO2 is actually just traveling in plasma. But the vast majority of oxygen, like 98.5% of the oxygen, is traveling on hemoglobin. In physiology, you'll learn there are 4 levels of protein structure. Hemoglobin is an example of a protein that has all 4 levels. That's why it says quaternary protein structure. Notice how red blood cells are not spherical. They are biconcave discs. I'll explain that reason why later. Quaternary means you have actual different chains making up one hemoglobin. In the case of hemoglobin, there are 4 chains that come together, 2 alpha chains, 2 beta chains. Each has a heme group in the middle. Looks like a flying saucer in this picture. Right in the middle of the flying saucer is iron. The oxygen binds to the iron. And when it binds to the iron, it turns this protein bright red. When it doesn't have oxygen, it's more like pale purple. Okay? Well, if there's 280 million of these quaternary hemoglobins in a red blood cell in this biconcave disc, each red blood cell can carry over 1 billion OTs. And if you've ever seen a blood smear, you'd be amazed how many red blood cells there are. Imagine 1 billion O2s in every one of them. And there's the iron in the middle, and that's what the oxygen actually binds to. So if you don't have iron in the middle, you have anemia. Your red blood cells cannot carry oxygen like it's supposed to. Anemia is a generic term that means less oxygen transport than normal. And that would be the most common form of anemia, iron deficiency anemia. All right, now when we say erythropoiesis, now this is red blood cell formation. Red blood cells only. And here on this figure that I got from the internet. They call the progenitor cell committed cell. That's the progenitor cell, proerythroblast. Basically, in erythropoiesis, what's going on in red bone marrow is the genes on this cell start turning off. There's only a couple that remain active. One to make alpha chains, one to make beta chains, one to make a couple of enzymes, carbonic anhydrase. Have I already said this to you? That everything is toxic? It's all based on dose? Basically, this cell is making itself sick with toxic levels of hemoglobin. It's becoming a bag of hemoglobin. When it gets to the normoblast stage, it's so sick that it decides to kill itself by spitting its nucleus out. The nucleus is the largest organelle in the cell. So it loses a ton of volume and it still has the same amount of plasma membrane. If you imagine a soccer ball, if you take a lot of air out of it, there's no way it stays a sphere, does it? It collapses. In this case, this soccer ball collapses into a biconcave disc. Does that now make sense? Okay. Well, there's still some rough endoplasmic reticulum and ribosomes that's still making hemoglobin in the reticulocyte stage, and that is the cell that spits out of the red bone marrow into circulation. Not the erythrocyte. This is what spits out into circulation.
If it spits its nucleus out, how is it able to like keep producing stuff and living? It's not, okay.
It basically becomes a dead sack of hemoglobin. That's not entirely true. It does have a couple of processes it does, but its metabolic rate is almost nil.
Why doesn't it just like go away then? Like how is it able to?
It will.
Okay.
All right, so if you take a blood sample and you see a whole ton of reticulocytes, it's called reticulocytosis, that's not normal. If you see that, what some things might be causing this? What would you be thinking about it yourself? Okay, this is a lecture of the living dead today. That's perfect for Halloween week.
Did it lose its blood supply?
What's that?
Did it lose its blood supply?
You're getting warmer.
It's dead, the person died.
No,
Their leg
no,
got
that
chopped
person
off?
doesn't make reticulocytes. That would be one possibility. Polycythemia vera is cancer of the bone marrow that affects red blood cell lines. What do you call it when it affects white blood cell lines? Leukemia. So this would be on the red blood cell line, polycythemia vera. But the problem is these are normal reticulocytes. If you have polycythemia vera, you have abnormal cells coming out of the red bone marrow. So no, that's a good try. But there's something that's different, related, called secondary polycythemia. This is what happens when you move up to Mammoth, and all of a sudden you're at 9,000 feet. You're gonna get a rush of reticulocytes, because now your body's trying to get more oxygen to tissues, and there's less oxygen in the air. The only way you get more oxygen to your tissues is you change that 45 to a 55, and plasma's now 45. While you're doing that, you're gonna get a lot of reticulocytes. So that would be one cause you're thinking is, well, maybe this person just moved up to the mountains. Or if they haven't, and this guy's in really good shape, and you ask him, well, what are your hobbies? And he goes, well, I like to do competitive bike racing. And you're going, holy shit, man, you're blood doping. Anybody with blood dopes is gonna have reticulocytosis.
What's blood doping?
Blood doping is when you cheat at sports
Oh, steroids?
by making this 55%.
Okay.
There's a couple ways of doing that. One, you can actually, before the event, 6 months before the event, take out a unit of blood, split, spin the plasma out there, just give your packed cells back to you just before the event.
Oh.
Another way is to give yourself a hormone called erythropoietin, EPO. This is actually, this whole sequence is regulated by this kidney hormone called erythropoietin. If you give yourself artificial erythropoietin, you're gonna have more reticulocytes. What else? Come on, people, this is critical thinking. Someday, somebody's going to depend on you having this ability. So start working on it now. And you don't get it by being passive. What happens if somebody bleeds a lot? What's gonna happen to that 45% if somebody's bleeding a lot? It's gonna go down because plasma is immediately replaced. For example, when you go donate blood, your blood volume doesn't go down. The volume is immediately replaced by interstitial fluid, but it takes a while to do hemopoiesis. So this number is gonna go down. Okay, so if you give a unit of blood, you're gonna see reticulocytosis as your body is working really hard to replace it. If you did not donate blood, then you gotta be thinking this person's bleeding. Wait, there's no blood on their sheets or on their clothes.
Internally bleeding.
They're internally bleeding. Everybody see what critical thinking you're gonna need someday?
What would happen to this if they were on like a blood thinner? Like a medication?
There's various forms of blood thinners. And, oh yeah, everybody look at me. Everybody look at me, because everybody needs to know that if you're going into healthcare. Blood thinners do not thin the blood. It is just as viscous as normal blood. Everybody got it? Everybody got it?
Yeah.
That's so that lay people will think the blood is thinner. You should know it's not, but you are going to do something about these guys. You're gonna make them either less numerous or less active or less able to create what's called a positive feedback loop when you're doing blood clotting. You are interfering with blood clotting mechanisms. That's what blood thinners do. Okay? Yeah.
So I've heard of people, getting their blood taken out, the plasma separated, and having it put back in. Is that the same thing as the sports guy you were describing?
There are PRP injections. We do that in my family.
Yeah, it's a form of pheresis, and there are reasons to that. For example, if someone needs platelets, platelets are just part of this tiny percentage. You need a whole bunch of blood out to get platelets out. It's called platelet pheresis. So they'll stick an arm, a needle in one arm, goes through this machine, pulls out the platelets, everything else goes back in the tube and goes into the other arm. Otherwise, you have to go through way too much blood to get this little bit of platelets here. Does that make sense? Any other questions? Yes?
What about those people who are on dialysis? Do they circulate the blood or?
And it's kind of the same thing. The blood goes out in one vessel, it gets filtered, gets the waste out, and then everything else gets put back in. Any other questions? This is what's going to happen in lecture exam form material, because now we get to actually talk about organ systems. So this is a good time to ask questions. Oh, here's the erythropoietin. So that whole previous slide is directed by this kidney hormone. These cells will release more EPO if you are in low oxygen. So if you have lost a lot of blood and this goes down, especially with, as it relates to this, you're gonna have more EPO coming out. If you move up to Mammoth for a while, you're gonna have more EPO coming out. Everybody got it? This is all negative feedback. Now, because this is basically a dead sack of hemoglobin, they can only circulate about 120 days. Every time they squeeze through a capillary, the plasma membrane can get a little tear in it. Because this is a dead sack of hemoglobin, it cannot repair itself. Does that make sense?
Yes.
Now, from last week in lab, I know you got lab exam 3 this week, so I'm not gonna waste too much time with this. In a lap around the circulatory system, say if you start from the right atrium, go all the way through and end in the right atrium, how many times have you been squeezed through capillaries? At least twice.
Twice?
From the right atrium, you're gonna go through the pulmonary capillary to the left side of the heart. Left side of the heart, you're gonna go through a systemic capillary back to the right atrium. Pulmonary capillaries, systemic capillaries, you get squeezed twice. However, what happens if you go through a portal vein?
Oh, yeah, more.
That lap, you're gonna get squeezed 3 times. Because the portal vein is between 2 systemic capillary beds.
Got it.
Okay? Well, after 120 days of it, it's just too many tears in it. Now it becomes a risk to your circulatory system. So you have macrophages in the spleen, liver, and bone marrow that take out roughened old red blood cells out. So you got this dead sack of hemoglobin that takes the hemoglobin, pulls out the heme group, recycles most of the iron, but not all of it, which is why you must have a continual source of iron in your diet to replace that which is not recycled. If you don't, you're gonna have iron deficiency anemia. Everybody got it? The globin is just a protein. Protein is split into the links. Remember, proteins are the chains, amino acids are the links, and your body's gonna recycle those links to make other proteins. Everybody see that in this figure? Yes.
When I was pregnant, well, both times actually, I ended up getting, I was anemic for both pregnancies, and is that because, the baby's taking a lot of my nutrients and the blood and everything, stuff like that? And that's why you have to take iron pills and stuff.
And also your iron metabolism changes during pregnancy as well. And if that is on top of any dietary changes that sometimes happens during pregnancy, that can complicate things too. All right, well, let's just talk about the experience of being human. See this heme group? It's gonna become different forms of bilirubin. After it goes through different forms of bilirubin, it's gonna become bile. And bile is gonna go out these ducts we're gonna learn about in lab, and eventually gets put into your duodenum, and it's gonna go through your small intestines and large intestines, you don't poop it out. Have you guys ever gotten that really bad bruise, especially if you played sports? Bruise that is so big and bad that by the time it fades, it's not even in the same place anymore. But actually gravity has drifted it. Have you ever had one of those? Did you notice that it changed its color?
Yeah.
You are watching this sequence. At first it's kind of a bluish purple, and then it kind of starts to turn this weird kind of greenish color. Now if it's a small bruise, you're not gonna see it. It's gotta be a big bad bruise where there's a lot of red blood cells out in the tissues. They'll end up breaking apart, and then your body's gonna do the same thing with other enzymes. It'll turn this weird shade of green, and then it's gonna fade into kind of this orangey yellow color until it just about when it fades, it turns brown, then it's gone. You guys ever seen that sequence? That's the sequence. And this is why regardless of the food you eat and its color, when that deuce hits the toilet, it's brown. You're watching the same thing. Does this make sense? And this is why when we look at the cadaver, why the gallbladder is green. It is full of bilirubin that has not been changed into the final bile yet. A lot of that change happens in the guts. Okay,
So what if they take your gallbladder out? What happens
what's that?
if you get it removed?
Oh, gallbladder?
Yeah.
Bile functions as an emulsifier for fats. Does it say that? I can't hardly read that. Yeah, it's an emulsifier for fats. Say in about a month, you can go to mom's house and have Thanksgiving dinner, which is usually loaded with a lot of fat, and you can digest it because the bile makes it into small little bubbles. The bile is actually dripping out of the liver 24/7. But you don't need it unless food, especially fatty food, is passing in your guts. And so the sphincter closes the tube and the bile backs up into the gallbladder where it is stored and concentrated. If you do no longer have a gallbladder, you're never gonna get this huge rush of bile when you eat a big fatty meal, which is why when you have the gallbladder, they tell you don't eat a big fatty meal. Otherwise, if you go to mom's house for Thanksgiving and you don't have a gallbladder, you're not gonna be watching football after dinner, unless you have a TV in the bathroom. All right, let's talk about platelets. Platelets are not full cells. They are cytoplasmic fragments of a full cell, and the name of that full cell is megakaryocyte. And each megakaryocyte can make about 4,000 platelets. Mega big karyonucleus, so this is a cell with a large nucleus. And this is why platelets are so tiny and why the counts in a normal blood sample is so huge. So when we look at blood cells, you're gonna see red blood cells don't have a nucleus, white blood cells have nuclei, but these little pieces are the thrombocytes, platelets, they're fragments, not full cells. And they function in hemostasis. Now that's not homeostasis like on the first slide. This is hemostasis, which is to limit blood loss when a blood vessel has been split open. This is how thrombocytes look in circulation. But once it sets up these positive feedback loops, they go from this nice smooth looking thing to this angry, pissed off looking thing. And they stick together. Okay? And platelets have two functions in hemostasis. One is the blood clot, which is the fibrin nets. Activated platelets will start a cascade of reactions to turn this liquid into solid fibrin. See where it's underlined? It used to be this, now it's actual threads, solid threads. That's the blood clot. The platelet plug is not the blood clot. The platelet plug is spackle on the vessel wall. Go ahead and fill in the blanks and All right, there are 5 types of white blood cells, leukocytes. So this, I abbreviated this, red blood cells, those are erythrocytes, these are all leukocytes. There are 5 different types. They are classified based on a combination stain that's been around for over 100 years called Wright stain. It has actually 3 different stains in it. The cells that absorb the stain into granules are said to love the stain. And the root word, one of the root words for love is Phil, like Philadelphia, city of brotherly love, okay? So if it absorbs the stain, the end of the cell's name will end with Phil, as in loving the stain. The 2 that do not absorb the stain, their names end with cyte, for cell. Everybody got it? The 3 granulocytes are neutrophils, which is usually the most common, which is why I listed it number 1. This stain has a pH of 7, hence the name neutrophil. It used to be called polymorphonuclear leukocyte because if you look at 2 neutrophils right next to each other, the nuclei can look very different. Many form nucleus leukocyte. What I would write next to this diamond is fast eater. These are phagocytes, so they eat things that are foreign. These are the first ones to show up. Unfortunately, they tend to get full. The animation there is showing a neutrophil actually eating a bacteria, and it actually takes it into the cell. Wraps around the whole thing, pulls it in by phagocytosis, which is a form of endocytosis, where you can actually see the solute. This is a bacteria. Then we have eosinophils. The stain is this red eosin. The neutral pH, the pH 7 stain is pink. This is red. And because eosin is acidic, these are also referred to as acidophils, like neutrophils, the pH is 7. Next to this cell, I would write picky eater, because it'll only phagocytize things that have already been tagged by antibodies. This is usually the second to least numerous white blood cell. The least numerous white blood cell is the basophil. This purple stain has an alkaline pH, hence the name basophil. So you see how basophil, acidophil, neutrophil kind of makes sense? These have vesicles of histamine as well as heparin. Do you remember histamine when we talked about dermal wound healing? And the first part of that essay in lecture exam 1 was tissue mast cells or any basophils in the area. Now because they are so rare, chances are basophils won't be in the area. But if it's circulating around in circulation and the circulation brings it to the area of injury, once it gets there, it'll spit out histamine to exaggerate the inflammatory response that the tissue mast cells start. So here's all 3 of them. Again, you can see little granules in there. Pink, red, and purple. Any questions? Okay, the 2A granulocytes end with Phil. And they are both the largest and the smallest of the white blood cells. Fill in the blanks, let me go over this. let's go over monocyte. It's the largest white blood cell, usually the third most common of the white blood cells. And it says, in bolded, transported form of macrophage. What that means is monocyte and macrophage is the same cell. If it's in the blood vessel, we call it a monocyte. If it squeezes out of the blood vessel to eat things that don't belong, it's called a macrophage. In this form is actually a free macrophage because it can move around. It's the same cell, just where is it located? In the blood vessel, it's a monocyte. Out of the blood vessel, it's a macrophage, free macrophage. Everybody got it? Lymphocytes are the cells of the specific immune response, and you can see we have B and T cells. That's what we'll call them instead of calling them B and T lymphocytes. Same thing. They're all lymphocytes. Now look at, this is normally in the circulation the second most numerous white blood cell. Everybody got it? But in the body, overall, it's number 1. Because it's in lymph nodes, it's in your spleen, not in circulation. So the whole body, you should write this next to lymphocytes. Whole body, this is number 1. Most numerous leukocyte in the whole body. But in circulation, it's number 2. Whole body, in and out of blood vessels, it's number 1. But in your pipes, it's number 2. Everybody got it? And if you want an easy mnemonic, because you notice I just wrote the first letters first. Because I used to play basketball until I just got too damn old. But in the last few years of playing basketball, new legs move even better. You don't have to know the exact numbers, that's what the internet is for, but you do need to know the white blood cells in order. Which one's the most numerous, which one's the least numerous. New legs move even better. So again, lymphocytes is number 2 in circulation, whole body is number 1. And here's some T cells attacking tumor cells. By the way, when I first started teaching, I used to tell people that this right here is going to be the major steps of advancement in cancer therapy in the 21st century. When I first started teaching in 2000. In 2005, there came out the first immunotherapies done on humans, malignant melanoma, by a group outside of UCLA, well, actually part of UCLA. Now you even see this on TV commercials. This is happening since the time I've been teaching. And you just watch. And here's the difference. You do surgery on a tumor, you have to get clean margins, which means you gotta cut out normal tissue to make sure you get the whole tumor. And you can only get so many of them. If you have too many tumors, you have to do chemotherapy. Chemotherapy is just targeting cells that divide fast. So even though, yeah, it's gonna target cancer, it's also gonna kill normal cells that are dividing. Everybody got it? That's why you lose hair and get muscles. When you have immunotherapy against cancer, these cytotoxic T cells will kill the tumor cell and right next to it leave the normal cell alone. This is cell-specific therapy, killing only cancer cells. For example, let's go ahead.
Obviously, we just have that in our body, or that's
Yeah.
something that you have, okay.
Yeah.
So our bodies can just cure the cancer on.
Oh,
its
in
own.
fact, that's actually what happens. Okay, you want to know something freaky? For a group this size, over 17 weeks in a semester, at least one of you, statistically, has had a seriously bad cancer change in your body. Who was the unlucky person?
I had breast cancer 4 years ago.
But I mean I'm talking this semester.
Oh, right now?
Right now, one of you has had a bad cancer change. Who's the unlucky person? Well, here's the normal functioning of our immune system. Your cytotoxic T cells take it out before it becomes a tumor, and you even know you had it.
Wow.
This stuff happens all the time. Your immune system takes it out. Cancer cells are somatic mutations, which means you do not pass on cancer to your kids. When you go to the doctor, why do they ask you about a family history of cancer? You can't pass on cancer to your kids.
It's your body's inability to get rid of it?
You pass on your genes to your immune system. And if you have immune defect, you can pass on that immune defect to your kids. That's why it's relevant for medical histories.
Wow.
This stuff happens all the time. Well, if it happens all the time, and our bodies get rid of it so you don't even know you ever had that change, why don't we take advantage of it in immunotherapy for cancer?
How did they figure it out?
Well, they've seen enough slides like this with tumor cells surrounded by cytotoxic T cells. So what UCLA did is they took 13 patients with malignant melanoma. Do you guys know what that is? It is the most deadly skin cancer. Bob Marley got it. The primary tumor, look at your pinky fingernail. The primary tumor can be less than a quarter of that pinky fingernail, and you're already a dead person walking. Because it metastasizes so readily, it spreads throughout your whole body. Well, you can't cut out all those tumors. And chemotherapy is gonna kill you. That's just bad stuff. So what they did was they found these tumors, scraped off the cytotoxic T cells, put it in growth medium and cloned them by the millions, and infused people with their own cloned cytotoxic T cells. And with 13 malignant melanoma patients, 7 showed no signs of any malignant melanoma.
Oh my God.
4 of them reversed the progression of their cancer so much that they can go back to conventional treatments, because here's the reality, those 13 were already dead people walking. They've done all the conventional therapies. They had nothing to lose, so they did this. 2 people did die. From that point on, this stuff has been going off. Okay?
Wow.
I don't know why we call that. Is that clinical stuff fun to hear? Go ahead, felony splice is the last topic. This and the RH is the last topic I'm gonna talk about for today. Okay, I have to cover some terms of immunology, but that's the only way to understand ABO and Rh phenotyping. Antibodies, again, are these forms of globulin plasma proteins. They are made by B cells, lymphocytes. They're actually made by lymphocytes. Anything that causes lymphocytes to make antibodies is called an antigen. That is a contracted term that means antibody generating. Antigen. Everybody got it? For the ABO blood typing, there are 2 surface antigens. It's called surface because they are on the red blood cell surface. A and B. If you have the A surface antigen, you have type A blood. If you have B surface antigen, you have type B blood. They are genetically codependent, so that if you have both, you have type AB. If you have neither, you're type O. There's no such thing as an O surface antigen, it just means you have neither A nor B. Everybody got it? Now, next to the first diamond where it says exception. Draw a line off to the side and write, not like the flu shot. The vast majority of things that your immune system makes antibodies for is like the flu shot. Well, this is an exception, so this is not like the flu shot. For example, this is the season right now where people are getting flu shots. Before the flu shot, you don't have antibodies for this year's anticipated flu virus. Once you have the shot in about 2 weeks, you do. Everybody got it? This is the exception. Without ever being exposed to type B blood, this has to do with the way our circulatory system forms. Those with type A blood will have anti-B antibodies in their plasma without ever being exposed to B-type blood. It's the exception. Those that have B-type blood have anti-A antibodies without ever being exposed to type A blood. O will have both. But if you look at the bottom diamond, AB will have neither, because no one makes antibodies to their own surface antigens. AB cannot make anti-A or anti-B because no one makes antibodies to their own surface antigens. Everybody see the bottom diamond? So does these 4 figures on the bottom match what's on the whiteboard?
Yes.
Okay? This has to do with blood transfusions and why us teachers, for people going into healthcare, must be sticklers for detail. Because if you give the wrong type of blood, you're going to have problems with agglutination. Now this is for what is referred to as packed cells only. You're not giving whole blood. If you give whole blood, you have to have an exact match, period. But if you're giving packed cells only, you have some options. For example, all the rows are set up by who's receiving the blood. All the columns are set up by who's donating the blood. Everybody see that? If you have O-type blood, since you have both anti-A and anti-B, you can't have any blood cells that have A or B. Otherwise they're going to bind together. That is called agglutination. They clump together, and since capillaries are only a single red blood cell in diameter, if they clump together, you're going to plug up capillaries. Everybody see the problem with that?
Yeah.
So O can only take O blood. A can take it from both O and A because there are no B antigens on those to clump with the anti-B antibody in their plasma. B can take it from O or B, and AB can take it from anybody. Now, I'm not going to get to Rh system, but for packed cells only, AB positive is the universal recipient. Can take any blood cells. For packed cells only, O negative is the universal donor. You can give it to anybody. But if you are giving whole blood transfusion, it must be an exact match regardless of blood type. Because you're giving the antibodies too. Yes?
So is that why when you have surgery, they draw your blood prior?
If they have enough time, you know, and they can put off the surgery until you can re-up your percentage, because they want you to have a normal percentage before they cut you. But yeah, they can give you your own blood, and then it's gonna be an exam. Okay. I'll do the